Oh, ho, ho, ho. Oh. Oh, wow. Dang, that's pretty cutthroat. That's really competitive. Wow, good job battling Storm. Just took initiative. Game teacher's pet. That's incredible. Yeah, well, you just wow, just went into action. Devil Honor. Request some shungite. Before the stream has even started. Look at that. They must be drowning in 5G radiation. Devil Honor, don't worry. In 1 minute, I will save you from the 5G. Yeah, exactly. Or Gath. Gath redeems it a lot. Yep, Kappa, that's right. That's right. Don't believe what you see on the internet about 5G. Actually, no, wait. Yeah, do believe what you see. Real. Unclear which one I'm supposed to say these days. Alright, let's get started, folks. Get that music playing. Alright. Hello, Anonymous Cowboy. Alright, students. Who is here? Terrible question to ask. But there seems to be 7 of you, so I'll wait for like a minute. But students, raise your hands. You want to go into the third eye today and visualize some Taylor polynomials. Raise your hands. You're here? Okay, yeah. Yeah, okay, just a human guy. Awesome. Nice emote. Okay, Math Mama raises her hand. Ah, what a great... There you go. Yep, awesome. Good. Everyone's raising their hands. Okay, so we're gonna go compute some Taylor polynomials and go visualize them using our neuroimaging technology. Okay? So first I need to remind you, what is a Taylor polynomial? Okay? Now, remember the stories. Learn from the stories and not from just the formulas. Always keep the reason why the concept comes up. You have some possibly scary function. Meaning, some of you don't even know how to like plug numbers in to the function. Think about it. If I told you, hey, what's sine of pi over 6? Oh, no. There's my note card. You can't even plug numbers in. But polynomials, you can easily plug numbers in. because you know how to multiply and add. That's why you really like polynomials more than scary other functions, like ln. What is that? So possibly scary function, and you're looking at a particular number, input, x equals a, some particular, you're looking at the function near there, trying to understand it. Well, there's an amazing thing called the Taylor polynomials, which are a sequence of polynomials which are in some sense the best approximation of the original function near that point. And here they are. I've written them out. The nth Taylor polynomial, which I just gave a name to. Here it is. This is what you fill in. You fill in this part of the worksheet, which is just a number. Then you fill in this one, another number. This one, number. Oh, this is a number here. This is number. Just fill these in and stop at the nth derivative. Stop there. Divided by n factorial. Students ask, why are there these factorials in the denominator? Don't worry so much. The reason is, if you take this polynomial and you ask, what is its third derivative at a? So when you do the computation, miraculously, it will exactly match the third derivative of the complicated function that we're trying to understand. If you go to the Taylor polynomial and you ask, what is the seventh derivative of this, the 10th Taylor polynomial? You do the math. Thankfully, because we arranged these factorials exactly the right way, thankfully when you do that, power rule 7 times, you end and you plug in a, you get the same 7th derivative. It matches as the 7th derivative of the original complicated function. That's why the factorials are delicately placed there, folks. Because of positive power rule, not anti-power rule. Positive power rule. That's the explanation. We want to match the various, the value, the first derivative, the second derivative, the third derivative. We want to match those with a simple polynomial rather than your complicated function. That's the strategy. That's where the Taylor polynomials are born. Okay? And here's the formula. It's not scary, it's beautiful, and it's simple, provided you know how to fill in the blanks. So let's go study some. We're gonna do some examples today. We're gonna do a scary function called e to the x at x equals 0. So a is 0 for us in this example. We're gonna go look at scary function sine x, and we're gonna look near x equals 0 again. We're gonna go look at cosine x. Very scary. We're gonna look at x equals 0. By the way, when you only look at Taylor series at x equals 0, for some reason, this dude named Maclaurin gets credit. You call it a Maclaurin polynomial when you only look at Taylor polynomials at x equals 0 specifically. This dude gets credit for the weirdest thing. You know what? I'll just do Taylor polynomials at 0, and therefore I am immortalized with a name. So when you see that in the homework, you're just computing the polynomial at 0. Okay, good. So to contrast that, I will then do square root of x, all right? At x equals 1. Not Maclaurin anymore. Maclaurin's bye-bye. Back to Taylor. All right, let's go do this. We're gonna have to go into the third eye, because we're gonna visualize these polynomials. I'm gonna show you. They are pretty good. They're really, really good. That's what I'm gonna do. That's what I'm gonna do. Let's go. All right, where do I go here? Calc 2, that's right. Okay, here we are. Oh, hello, 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 hello. Math Mama, Battling Storm, Just a Human. Which one was Teacher's Pet? Battling Storm. Awesome, Teacher's Pet. Wow, that was theatrical. Go Pokes. Wow. Bro, Tropical Heat. Awesome people. My favorite people in the whole world are here witnessing this lecture inside my mind. Okay? All right. Let's compute the various Taylor polynomials of e to the x at x equals 0. Everyone can see my mouse, hopefully. Okay, let's do this. First example. Everyone get your note cards out so you know how easy it is to compute these Taylor polynomials, at least for the homework. First example. F of x equals e to the x at x equals a. Compute as many Taylor polynomials as you can. What? 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 There's a raid. Hey everybody. Whoa! Whoa! That's PogChamp. Hello folks, I'm sorry, I'm stuck in the seat of my consciousness right now. So I can't come out right now. But thank you, Prof. Pete. Professor Peter. Thanks so much. Awesome. All right, let's remove that because I don't want that on YouTube, you know? It'll just ruin my reputation, folks. Can't go ruining my reputation. There we go. We're gonna compute the Taylor polynomials of this here function at x equals 0. Okay, the yellow has changed. Okay, here we go. Grand formula. Oh, link my YouTube in the description. Okay, how do I do that? Okay, you do that. Just go to Peter's YouTube, everyone. Yeah, there you go. Look at that. There you go. Awesome. I hope that's not a Rickroll, but anyway. So keep going. So F and okay. So there we go. We're gonna fill this in. So how to fill it in? You fill out a worksheet, folks. Worksheet. The name of the worksheet is Figure Out Fn of A. The nth derivative at A. You're gonna have to figure out all of these. And the way to do this, the method for now, is do a couple and look for a pattern. All right, that's the best I can that's the best I can teach you, folks. So here we go. Luckily, I chose a really nice function. F of x is e to the x. Okay, I'm gonna fill out this worksheet. All right. What is f of 0? I don't know how to write a worksheet. I'm gonna try. What is f of 0? Okay, our function is e to the x. E to the 0. 1. Okay, good. Done with first part of function worksheet. Hey, what is the first derivative? Okay, well, conveniently, the derivative of e to the x is e to the x again. Oh, and then you plug in the point, the Maclaurin point. Let's call this This is the Maclaurin constant. Might as well, right? Might as well give him even more credit. This is the Maclaurin constant, and we're gonna plug in 1 now. 0 now, and you get 1. Okay, next part of the worksheet. Okay, plug in the Maclaurin constant. Wow, let me do this real fast. I'm sensing a pattern. I'm sensing a pattern. Look/hope. Look and hope are the same word. Okay? 1, 1, 1. Okay, awesome. Awesome. So, let's write out the first couple Taylor polynomials. 1 plus 1 times x minus 0, which is just x, folks. 1 plus 1x. T2. 1. This is f of 0. This is f prime of 0. Wow. F of 0 plus f prime of 0 plus f double prime of 0, which is 1 again, over 2 factorial, which is just 2 times 1, x squared. Awesome. 1 plus 1x plus 1 over 2 factorial x squared plus 1 over 3 factorial x cubed. Amazing. 1 plus x plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4 over 4 factorial, etc. We've got all of them in our hands. Here they are. This T1 is old school. This is the equation of the tangent line. T2, this is, what the? Wait. I'm stuck in my third eye. Thank you. Frecht Chemist. Everyone go check out Frecht Chemist. They do real chemistry with freckles and fun. They were in a lab the last couple days that I checked, which is exciting always. So go check them out, follow, and be friends with my friends. All right, I'm gonna have to remove this because Frecht is cool and stuff, but I don't want to, I don't want to be permanently associated with her. So let's just move on here. Let's move on. Okay. All right. So here they are. What is T2? T2 is the most tangent. The most tangent parabola for this function at this point. T3 is the most together cubic, the best cubic that you can choose, which looks the most like e to the x at x equals 0. Okay, enough of this talk. Enough of this talk. Let's go graph this stuff, folks. Here we go. New graph, e to the x. This place, this place is my consciousness, folks. But the person who can program and extract these images from my mind is my little brother. Much love to boring Professor Servant. Here's our e to the x graph. Let's increase the range here, which we can do with this technology sometimes. Okay, well, sometimes, okay, remove this. Okay, sometimes, gotta press enter a couple times in the right order. Okay, there you go. There you go. There you go. Here's our e to the x graph. All right? Okay, so now we're gonna add a new graph Hold on. We're gonna add a new graph. So here's e to the x. Whoa, check that out. What a beautiful exponential graph. Beautiful. Let's graph, add new graph. Let's graph the first Taylor polynomial, which you can see in the background, sort of. It's on your piece of paper. It was 1 plus x. Let's graph this. Boom, tangent line. This, I told you, that's the tangent line. Taylor polynomials just generalize the concept of a tangent line. There it is. Okay, let's look at T2. 2 factorial is 2 times 1, which is 2. Okay, I'm gonna put that in the denominator. Oh, wow! Check out this beautiful parabola here. Boom, coming in, coming in. It's a parabola. It's trying to be this exponential function, and it's really, really good right here at the point x equals 0, y equals 1, the output point. Yeah, but if you zoom really close, you'll see that the parabola is only equal at this one point, but it's really, really close for the longest period of time. That's what distinguishes it among all parabolas. Fantastic, folks. I'm gonna keep going here. Let's do x cubed. Let's add a cubic term. Let's look at the third Taylor polynomial. Now, 3 factorial is 3 times 2 times 1, which is, if I did it right, 6. Okay, wow, check out this cubic. Okay, we gotta squint. The cubic is the one on the outside. Come in, come in. Nice cubic function. Wow, I can't even tell the difference right here. And then it diverges. It diverges and it keeps going on with its life. T3. Okay, let's zoom in. Look at this. Can you tell the difference? Very hard to tell. But if you zoom in far enough, there will always be a little bit of a crack between the cubic polynomial and e to the x, and they'll only come together at this one point. But the cubic is the best among all cubics. Look. I'll change this coefficient a little bit. Like, let's change it to 5. Oh, see that? It kind of, look at 5. This is 5. Now I'm gonna go to 6. Ooh, see that? It's tighter. Tighter. Okay, let's make it like 10. Oh my god, look over here. Look over here, folks. It goes, and then it goes onto the other side. It like seeps onto the other side. That's so bad. That's so bad. Ugly. Look at this. Look at this garbage happening here. That's so bad. Okay, let's go back to 6, which is the correct cubic polynomial. Cubic Taylor polynomial, T3. Beautiful. Okay? Okay, we can add the 4th power. Just so you see it in your face right there. You have to witness this. 4 factorial is 24. Whoa! Oh! I can't... Which one is which? Well, I mean, the one that stops is the degree 4 one. We come down. We come down. What is even... Oh, what is going on here? I can't even tell anymore that they're different in here. Okay, yeah, then the degree 4 polynomial, it's a polynomial, so it goes back up. Okay, so it's not gonna be able to stay with e to the x forever, folks. These are polynomials. These are not literally e to the x. It's our best attempt. Okay? Great. All right. What's going on with this screen? Why am I stuck in a blurry... Okay, folks. That was the first example. Math Mama, Battling Storm, all of you folks. Welcome. Okay. I think I need to reboot this thing for some reason, so I'm gonna do that. All right, folks, newcomers, thanks for showing up. I'm stuck in the middle of my class, so I will not entertain you. All right, so class, that was my first example. Let's move on to the second example because it'll teach us something. All right, so we know how to compute the Maclaurin polynomials of e to the x at x equals 0. And so now you can basically do half the homework already. It's filling out that worksheet. Let's fill out the worksheet for sine x. Let's do that. That'll be fun. Let's go. I have a 45-minute class, folks. Let's just cram this all in. Sine x. Boom. Next example. Let's compute. Let's compute the Macdonald polynomial of f of x equals sine x. That means Taylor polynomial at x equals 0. Okay, let's do that. Worksheet. So here's our function. Okay, I gotta find all the derivatives of that function, all the nth, 10th derivative, 11th, and plug in x equals 0 all the time. Maclaurin's constant, x equals 0. Okay, so let's see. F of x is sine x. Great, good start. F prime of x is cosine x. F prime of x is the derivative of the previous answer. Amazing. This is just incredible. F triple prime is, keep going. This is just amazing. Okay? F quadruple prime F quintuple prime. Okay, F sextuple prime. I sense a pattern. In fact, every 4 times, you're just gonna copy paste. All right, I'll do one more. Okay, and okay, the worksheet is, yeah, go ahead and compute these and plug in the Maclaurin constant. Don't forget, you're gonna get numbers at x equals a, which is a is 0 for us. Okay, so let me fill out that worksheet. This sine of 0 is 0. At 0, this is 0. Cosine of 0 is 1. Is 1. Okay. Negative sine of 0 is 0. Negative cosine is -1. And it's just gonna repeat, folks. 0, 1, 0, -1, 0, 1, 0, -1. Spam it in the chat. 0, 1, 0, -1, 0, 1, 0, -1. Pattern. There you go. There you go. There it is. There it is. There it is. Good job. Okay? Awesome. So now, let's go fill in the Taylor polynomials. So, pay attention, folks. Something funny happens here. And that's why I wanted to show you sine's example. T1 is 0 plus 1 times x. Okay, so it's just x. T2 is 0 plus 1 times x plus 0 times x squared. Lesson. The quadratic Taylor polynomial doesn't actually have to be quadratic. there could be a 0 in the coefficient of x squared. That can happen, folks. And you're seeing one example that happens. We still call this t sub 2 though. Confusing. But we still call it that. Just to be systematic with our numbering. 0 plus 1 times x plus 0 times x squared minus 1 times... Oh, there's a 2 factorial here. Yeah, is someone telling me I'm missing some factorials? Yeah, I know. Okay, I fixed it. Okay, there. Let me write it out. X minus x cubed over 3 factorial. Don't forget your factorials, folks. The third Taylor polynomial is truly degree 3. That's interesting. That's good. That's what we're used to. Okay. The fourth one, though, is not actually a degree 4 polynomial. There's clearly an even and odd thing happening. And so let me write for you a huge Taylor polynomial for sine x. Okay? Look. This is T9. But weirdly, it's also just a little bit, because T10's x to the 10 coefficient will be 0 again. I just wrote out this pattern. I called this pattern, I just started writing it out, and look, it's beautiful. Notice things. The sign alternates. And you skip only odd powers with odd factorials. That one is for sine. Spam PogChamp if you want to see this sine x versus its Maclaurin polynomials inside of my mind. If you want to see that, spam PogChamp right now. Crickets. Oh, yes, yeah. Dr. Young's lab is here. Shout out to Dr. Young's lab, please, etc., etc. Awesome physical chemist. Teaching all kinds of amazing things out there. Okay, yada yada yada. That's good feelings and everything. Okay, boring grapher. Here we go. Third eye technology. Here we go. Here we go. Here's our various Maclaurin polynomials. And now I'm going to graph sine x first. What the heck? There you go. Sine x. Let's increase the range, folks. This works half the time, so let's see. Awesome. Okay. Great. Here's sine x, our beautiful sine x graph that you're used to. We are focusing on this part of the graph, the part that's flickering for some reason. You know, the part that's flickering? You're focusing here because of Maclaurin. Okay, now we're going to add a new graph. Let's look at the first Taylor polynomial, which was just x. Of course, folks, that's just the tangent line. Boring. All right, let's look at the third one. Because why? The quadratic one is secretly just T1 again. So let's go cubic, folks. 3 factorial is 6. I got the minus sign right. Boom. Oh! Look at that beautiful cubic. It comes in. Look at that. Oh, perfect. Perfect. Look at that. Look at how good it is. Now you might ask, what's the point of all this? Hey, students. Students, would you rather have an integral problem that has this cubic? Would you rather have an area under curve problem that has this cubic? Would you rather have any math problem that has just adding, multiplication, and division rather than this garbage, which you don't even know how to plug in without your note cards? Gee, I wonder. I wonder what's the use of all this. Okay, next, let's look at the quintic. Quintic, degree 5, Taylor Maclaurin polynomial. This is awesome. Okay, what is 5 factorial? 5 times 4 times 3 times 2, carry the 8, and then subtract. Okay, 120. All right, there you go. That's 5 factorial. It's a plus sign because of the pattern that you guys spammed in the chat. So this is this. E5. Let's look at it. Ready? 1, 2, 3, 4, 5. Because it's the 5th one. Okay. Oh, wow, look at this polynomial. Check it out. It's so good. It's so good to sign. This polynomial is so good to sign at this point. This polynomial is completely garbage for sine of x over here at this point. At this point, look, over here, I can't even see the Maclaurin polynomial. Where is it? Oh, it's way over there. Oh my god. But look over here at this x equals 0 point. Which one is which, folks? I can't even tell the difference. What's going on here? Awesome. Hey, Just a Human Guy, all of you. Thank you for being here and witnessing the awesomeness of that specific polynomial. This one, where I stopped at 5. This is one of the best. This is the best degree 5 polynomial for sine of x at x equals 0. Amazing. Okay, let's keep going, folks. Let's keep going with my stupid lecture. All right, so done with this. Back, teaching. Okay, so I promised you more examples. Yes, yes, Phi Gamma, you're sleeping. You're so cool to sleep through class. The cool kids were the ones that slept through class and became uneducated. Yeah, cool. Okay, next. Let's keep going. All right. More examples. I'm going to zip through cosine. So this is the Macintosh polynomial. Okay, so we're gonna do this. I'm just gonna tell you, when you fill out the worksheet, which you should do on your own, you will get the following pattern. You will get 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus x to the 8th over 8 factorial. So what do I mean by this? For example, this polynomial is t sub 8 for cosine x at x equals 0. Now, confusingly, it's also t sub 9. And all we're saying is that the 9th derivative at 0 is 0. So that coefficient, when you plug it into the Taylor polynomial formula, it's just a 0 in front of x to the 9. Okay? So cosine uses x to the n over n factorial for the even n's and alternates them. Sine does it for the odds. And I think you're starting to get a hint as to where the name odd and even function might be coming from. I don't know. I don't know. I have no idea. All right, so this is what you'd get. I'm gonna skip this example. Let's do square root of x at x equals 1. Let's do more fun. let's look at f of x equals square root of x at x equals 1 now. This is no longer a Maclaurin thing. It is a Taylor polynomial now. It's all the same, folks. It's just looking at different points on the curve. Okay, worksheet. We gotta do the worksheet of nth derivatives. Okay, the original function was square root of x. Good. Okay, first derivative. Power rule, huh? You're gonna make me do the power rule at this time of the day? 1/2 x to the negative 1/2. That's f prime. Okay. F double prime. Power rule again. What? Okay. So this is negative 1/4. Whatever. Sometimes it doesn't. You don't want to just go simplifying things unnecessarily too early. So I just did it for, I don't know why. I don't have free will. Okay, next. Minus, boom, boom. Okay. Go on, keep going. I can do this. Etc. Oh, it's negative this time. So on and so forth. Maybe you see a pattern, maybe you don't. But what I'm gonna do right now is I'm gonna stop here, plug in x equals 1, and see what these Taylor polynomials look like versus this scary function, square root of x, that you guys barely know how to deal with. So many wall of shame things happen with square root of x. We know. We've been there. Okay? Alright. So square root of x, plug in x equals 1. Don't forget. So we get this is 1. Square root of 1 is 1. This is 1/2. 1 to any power is 1, folks. So this is 1/2. This is negative 1/4. This is positive 3/8. And this is negative 15/16. Let's put them all in the handy-dandy formula. The grand formula of Taylor expansions. Taylor polynomials. Okay, so T1 is this plus this times, careful, x minus 1 like that. If you don't include the minus 1, you'll just be wrong. That's it. I don't need to explain that further. If you don't include it, and you graph it, it'll look nothing like the tangent line. There, that's enough of an explanation. Okay, so there you go. Keep this 1 in there. Don't forget it. All right, you can collect like terms and FOIL and all this garbage. Just leave it. It's beautiful. It's just 1 plus 1/2 times x minus 1. There. Why do you want to do stuff to it? Okay, T2. Okay, it's 1 plus f prime over 1 factorial. That's just f prime. Minus 1/4 over 2 factorial times x minus 1 squared. All right. This is the second Taylor polynomial. Let me do some math to it. 1/4, blah blah blah, boom boom boom, a little bit of 1/8. All right, that's T2. T3. Notice T3 is T2 plus the next term. So you just copy paste this. Okay, plus or minus, I don't know, plus 3/8 over 3 factorial times x minus 1 all cubed. All right, this is enough. Let's go check it out. Let's go check out square root of x at x equals 1 versus these amazing polynomials that are the best for square root of x at x equals 1. Let's go. I gotta put on my fMRI thing. Calc 2. Let's go. Here are our functions. And we're looking at square root of x at x equals 1. Beautiful. Beautiful. G. All right, new graph. Square root of x. Wow, what a beautiful graph. Okay, let's increase the bounds, okay? Oh, this is stupid. This is dumb. Why am I increasing the negative bound? I'm a dumbo. Okay, there you go. Incredible. Check out this function. Where is it? Okay. Here's your sideways parabola, positive part. And we are not focusing in this purple part. It's purple because red plus blue is purple, I'm imagining. Though, Dr. Young's lab will tell you exactly why blue and red form this color. I've been told that this color doesn't even exist. Okay, anyway, you can learn more about that from Dr. Young's lab. Now, we're focused here. Right here. Does this help you, students? Good. We're focused here on this function because this is at x equals 1. Awesome. Now let's introduce those things we just computed. New graph. Let's do T1. Just to make sure we didn't do something stupid. Check your notes. Don't let me do something wrong. All right. 1 plus a half times x minus 1. I'm gonna press enter and I'm gonna hope I didn't do anything wrong. Wow! I didn't. We succeeded, folks. That does look like the tangent line. Awesome. That means we did that first computation right. Okay, next. Minus 1/8. Oh gee, I really hope I did this part right too. It's always dangerous to do these kinds of stunts like live, especially in front of thousands of viewers. So, okay, so here we go. Let's look at the second Taylor polynomial of the square root of x at x equals 1. What a mouthful. Amazing. You see this? You see this parabola? Vertical parabola? It is the best one among all parabolas that go through this point. The best for square root of x. The most accurate. It's this parabola. That's incredible. Let me increase the resolution if that does anything. Incredible. Look, can you tell the difference? I sure can't. Okay. Next. Let's introduce the cubic term. Plus, oh boy, 3/8 divided by 3 factorial. Oh, E? E. Press E? Oh, oops. Okay. Well, anyway. So 3/8 divided by 3 factorial is hold on, let me just do that real fast. 3 divided by 48. Is that right? Is that right? 3/8 divided by 3 factorial is 3 over 48. Okay. Right. Okay, there you go. So let's do that. 3 over 48. Star x minus 1 cubed. Amazing. Plus sign. Get the signs right, everything. Here's our cubic t sub 3 for square root of x at x equals 1. Enter. Wow. Look at that beautiful cubic polynomial. Okay, apparently if I press E, and then how do I zoom out? Q. Okay. Look at this cubic polynomial. Boom. Coming in. This cubic polynomial definitely looks like a cubic, but it is the best cubic for square root of x at this one point. Here. Here, I cannot tell. Can you tell? I can't tell. What's going on here? Look at that. Look. Best cubic for this function, square root of x, at this point. This function completely sucks over here, folks. But it's really good where I'm concentrating. Okay. Let's get out of here. Folks, oh, there's only 1, 2, 3, 4, 5. Oh, Gath is here. Great luminary. Wow, I was gonna say there's only 8 people here, 9 or whatever. I can't count this, but Gath counts like with multiplicity. Gath is a great being. Wait, what the heck? Okay, now see, that's the power of Gath. When Gath is here, everybody else follows. That's just how it is, folks. All right. Hey, math guy, how's it going? Okay, let's get out of here. I've done enough for today. I've finished the material that I wanted to talk about. And we're going to wrap things up now, folks. Time to wrap up. I'm going to wrap up. So, what did I promise? I promised Taylor polynomial computations. Here's the general formula. All right? Okay. I did some examples. I hope that was enough for you to do your homework now. It should be. We still have Friday, where we can tie up loose ends. But on Friday, my main focus will be to try to address the following question. Friday's topic is a little bit painful for students, but the underlying question is completely natural. How much error happens when you swap a complicated function, you know, the ones that you don't even know how to plug into without a note card, or its Taylor approximation at a given point, x equals a. How much error? How exactly, like not exactly, but like, can we measure? Can we get any clarity on how bad this trade is or how good it is? Be an optimist. We'll learn how to bound the error. How the Taylor polynomial cannot get too far from the actual function when you're concentrating at a particular point. That's the lesson on Friday. And I'll show you how to like, how to get a handle on this error, this potential, this error that comes up. That's the issue on Friday. Okay? Fun times. Okay, this one is so boring. Region dependent. Okay. Fascinating. All right, so I'm just gonna read the chat. And one more announcement, but I'll make it on Discord. It's a sad announcement, but I do have to make it. So here, class, here's the announcement. This. Okay. But use each other here. There you go, students. Go ahead and check the Discord for the sad announcement. Okay? All right. Okay. All right. Now I'm gonna go look through the. I'm just gonna quickly browse through the probably degenerate chat and see if there's anything I need to address. See if there's any people I need to ban instantly. Let's go check. Okay, lots of attends. Good. I liked attendance today in my third eye. We know who the brains behind the operation is. Technically, Anonymous Cowboy, I am the brain behind the operation. Cowboy67 tries to make a snarky comment. They say, hey, boring professor servant. We know who the brains behind the operation is. Implicitly saying that boring professor servant, my younger brother, who's obviously quite awesome because they created this thing. They are not the brains behind the operation though. Quite literally, this brain is being scanned by the technology. So please be careful with your words. All right, so there was a recorder that was redeemed, and who redeemed this recorder? None other than Smash Time Fools. So Smash Time Fools is a great luminary. Smash Time Fools is a hardcore mathematician. Does fractal math. I mean, to put it, you know, to maybe possibly insult it. Oh, Just a Human Guy also redeemed. Just a Human Guy is also incredible student. And will one day become a mathematician, I'm sure. So yeah, great luminaries requested some recorder playing. I'm gonna play some stuff for you. I'm gonna play, let's play some patriotic music, okay? Okay, I mean, it's politics is in the air. Let's be proud. Proud patriots. Okay? Awesome. There's no law against completely butchering one of these songs, right? I hope. Jeez. Okay, this video is not going on YouTube. I hope they don't come after me. Okay. Let's see what's happening. Let me go through the chat again. 1001 minus 1. Good. People. Midichlorian is the powerhouse. Midichlorian is the powerhouse of the cell. Is he saying midichlorians? Wait. Okay. If only I read the chat while it actually happened. You know? Wouldn't that be great? But I can't. I can't do it. Alright? These aren't Macaulay Culkin polynomials, yeah. We need proof. Oh. Alright, good. Okay. Midichlorians. Bro, it's midichlorians. Midichlorians are the powerhouse of the cell, bro. Alright. Diatom's attack? Tropical Geek? Alright, we'll go to Diatom's attack. Alright, All right, folks. Bunch of voyeuristic strangers out there. Thanks to you, but primarily thanks to my students. And students, we are entering difficult terrain as the class proceeds. So you need to huddle up, produce great camaraderie in the Discord, discuss confusion, talk to each other, use the homegrown Chegg channel, become a general when I ask for it. Very important that this happens, and more through the semester. Okay? All right, so let's get out of here. Let me show you to Diatom's attack. A great, microscopically great streamer. This person is microscopically great, if that's a term. All right? Here we go. Let's see. Diatom's attack. Diatom's attack. Go spread the joy of Taylor polynomials. Go spread the joy of Maclaurin polynomials. Go educate people on Maclaurin's constant. Let's popularize that too. Why not? Everybody gets a constant. Okay? Maclaurin's constant. Maclaurin's. Midi-chlorian's constant. Alright? Diatom's attack. Go spread that knowledge. Here we go. They're probably gonna be looking at some bizarre, made up, like, little CGI garbage. So just humor them, okay? Just nod your head and say, yeah, this is real, of course. Yeah, sure, if you say so. Okay, yeah. Alright, bye.
My god, it's a raid from Boring Math Professor. Look at all these people he brought into our channel. Suddenly we have massive numbers of people.
Hurry, someone tell us what a lichen is. Please.
The metachlorian.
I know. Tropical gig!
Hello Boring Math Professor, how's it going?
Do they do math in his streams?
Lichens are fungi that live on trees. No, that's not right.
It's a fungus and...
It's made of two things.
A protozoa.
Symbiotic relationship. A lichen, not a lichen.
Lichens are fungus and...
Give us an option.
You're supposed to
Algae.
answer.
A fungus and an algae?